Okay, so in a previous video, I probably talked about the three key elements for a programming language, or really any language whatsoever. That's primitive elements, so in a programming language, that's things like numbers or primitive operations. There's combinations, so complex expressions that creates this incremental complexity, kind of like nested combinations and regular combinations that we saw in the last video. But now what we need is the third part, which is abstraction, which takes that complexity that we build by combining things and simplifies it again, making the result of that abstraction essentially primitive elements in a higher level of complexity. So the first type of abstraction we'll see, and we'll see many throughout the course, but the first type that we'll consider here is symbolic abstraction. So symbolic abstraction is the use of names to refer to computational values. So in Scheme, we'll use the keyword define to create bindings between a name and a value, essentially creating a variable. So for example, I could say, let's do it down here in the REPL, define x to be 5. So keyword define, then some symbol that isn't yet bound. We're going to create a binding for that, and the value that we want to bind to that. So this creates a variable called x that has the value 5. So if I ask what's the value of x, now it refers to the value of its binding. Okay, so in Scheme, this is a little bit different than the assignment operations from other languages. Variables are effectively constant once we've declared them, at least for now. We'll take a look at softening that rule later on in the course, but for now, when we create a variable, we're effectively creating a constant. It's a variable in the sense that it's a stand-in. We're using a name in place of a value, but it's not variable in the sense that it's changing. Okay. So if we use define twice, so if I said define x to be 6, it's going to destroy the old binding and create a brand new one. That's an important distinction. This immutability will show up later on. It's what prevents side effects in the language, which you might recall me mentioning is an important feature of functional programming in general. So once we create variables, they're effectively constants, but they're still quite useful. We're going to use them to refer to values rather than having to memorize all of the values. But first, let's talk about the variable name rules, or some of the conventions for variable names as well. So first off, all variables need to be made out of basically pretty much any of the letter and number characters. So all the uppercase, lowercase, and digit characters. So if I just keyboard spam here, that's a valid variable name. Probably not a very good one, but technically valid. Okay, so any of the basic characters. We're also in Scheme allowed to use pretty much all of the symbols. Okay, so we can have a variable called x exclamation, which maybe we want that, or maybe x interrobang, and then it has a different symbol there. So we're allowed to use exclamation, question, here I'll just type them all out, dot, plus, minus, times, divide, less than, equal, greater than, colon, dollar sign, percent sign, caret, ampersand, underscore, tilde. Any of those. The underscore doesn't show up right now. I think that's just the recording, but there's an underscore there. Great, so any of the symbols can go into your variable names, and it's commonplace to use some in certain places. We'll talk about conventions as we come across them. Importantly, though, you can't use spaces in your variable names, so I'll just get rid of this underscore. I don't know why it's coming out blank. Yeah, so any of the symbols except for spaces, though in general, you shouldn't start a variable name with a plus or a minus. It's technically allowed, and it will work in some implementations of Scheme, Dr. Racket included, I believe, but it won't work in others. So again, if you want your code to be portable, make sure you're not including plus or minus as the first symbol in your variable names. Okay, and the last rule here is that they are not case sensitive. So if I define something, if I define, say, define G to be 3, and then ask what's the value of uppercase G, it has the same value. So case insensitive completely across the board. All right, so that's the variable name rules. Let's move on to discussing abstraction a little bit. So as I mentioned, symbolic abstraction here is the use of names to refer to computational values, but abstraction in the general sense is the idea that we have some complexity and we want to simplify that. So defining a binding here is a simple means of abstraction because we're taking those complex ideas, or the values that we've computed, perhaps very complex values that are the result of many computational steps, and we're going to assign a simple or meaningful name to them. So we're hiding all the complex values behind this simple name, thus abstracting the effort of remembering the values themselves. So it simplifies programmer effort. So for example, I could say something like define pi to be 3.14159265358.9. Yeah, and then anywhere I want to refer to pi in my code, I can just say pi rather than having to actually type out the whole thing. Right? The program only has to remember the name instead of the calculation or the value. So in that sense, it simplifies complexity because it reduces the amount of things we have to remember. But the abstraction goes beyond that to abstracting or let's say creating a separation or an interface, some sort of division between the values, how they're constructed, what they exactly are, and the meaning, how they're actually used. Right? So pi is generally speaking used in certain situations where the difference between the circumference and the radius is necessary. Sorry, the ratio too. But how pi is calculated is essentially a matter of preference or whatever our current objective is. So we could, for example, define pi in a bunch of different ways. It doesn't matter. Oops, can't type today. Doesn't matter how pi is defined. We could define it that way, or we could say define pi to be divide 355 by 113.0. It's a pretty good estimate of pi. Or if we don't care that much, we could say define pi to be a lesser estimate, so 22.0 over 7. Right? And it doesn't matter. When we come down here and we start using the value of pi, it's going to be the same, or relatively, let's say semantically the same. It'll still refer to the same value, whether it's an accurate estimate or not. So the idea being we're abstracting the usage of pi away from the actual value of pi, and that frees us up to change the implementation of those values. And it's not just pi, obviously. Anywhere where we have a variable, we're separating what's inside that variable from how that variable later gets used. Okay. And this, of course, also supports incremental development, something you've probably seen in your other courses using languages for 2.5 years of computer science already. So supporting incremental development means once we have this variable, so once we have pi, for example, we can use pi. Let's define another variable here, radius. And then we can use pi and the radius to create a circumference, or to calculate a circumference. So we'll say the circumference is 2 times pi times the radius. Okay, whatever that happens to be. And we can save and run this. Oops, don't need to save right yet. Just run for now. And then I can ask, what is the value of circumference? And it has a value through some sort of calculation. And then circumference, which is defined in terms of other named values, can then be used further on down the line. So maybe we can define some variable height, we'll say is 20, and then we can use that to calculate the area of a cylinder. Let's say define area cylinder, and the area of a cylinder is the circumference times the height plus 2 times pi times the radius squared. So I'll just say radius times radius. Oops, sorry, I keep hitting save instead of run. There we go. And we can ask what's the area of the cylinder. And there it is. It's an arbitrary cylinder, so the number doesn't matter. The point here is, if you look at the calculation for that cylinder, that reflects pretty similar to the actual formula for calculating a cylinder, right? It reads pretty straightforwardly. So circumference times the height plus 2 times pi r squared. And you can get that almost from the text itself. Compare that to what would happen if we didn't have variables in this case. We'd have something like define area of the cylinder, which would be still have similar operations. Instead of circumference, we'd have 2 times pi times radius. Instead of height, we'd have to put in 20. Instead of pi, we'd have to take in, let's say, this calculation here. There we go. Instead of radius, we just use the constant 10. And we'd have to do the same for the other side as well. Is that the right one? Yeah, there, okay. And then we take all of this, and we have to substitute all those values as well. So there's that calculation. Instead of pi, we again have our estimate of pi, which has to be calculated again, so extra work on our processor as well. Instead of radius, we'd have to put in 10s here as well, 10 and 10. Now, these two values should be the exact same. I'll call this area cylinder 1 and area cylinder 2. Sorry. Python habits, save and then run. Right. So in this case, if we want to know what the values are, we can ask what is area cylinder 1 or area cylinder 2. They have the exact same result, but one of them looks or reads much like the formula for calculating the area of a cylinder, whereas the other reads much more like a jumble of numbers and operations. So the abstraction here hides the complex values behind a simple name, which then supports incremental development where those simplified names like circumference and radius become the building blocks for higher levels of complex combinations. All right. So one more point while we're here talking about variables, and that's the notion of type checking. Let's go back to the notes here. So type checking is the language's process of enforcing correct kinds of values are used for specific operations. Right? It's a way of ensuring that the operator is applied to the correct type of operands. So we can't divide a string by a number, for example. It doesn't make sense. Some sort of type checking has to determine that it doesn't make sense before we attempt to do these operations. All right. So there's two flavors for type checking. There's static type checking and dynamic type checking. In static type checking, the type check is done at compile time. So all the variables have what's known as static types because those types don't change. So static in the sense that they're not moving. So all variables that you create need to be declared with this fixed type. Something like Java or C, for example, where you'd say int x instead of just x to declare your variable. The nice thing about static type checking is that it does prevent simple type errors from crashing your programs because it's something that the compiler can see from the code itself. Your variables aren't changing in type, so right at the outset, we know what operations should apply to those variables. And it's commonly used in compiled languages for that reason. We're going to read through the whole code, make sure it all works, and then I'll give you an executable. On the other hand, there's dynamic type checking, where the type of the variable is not constrained, and the type check is done at statement execution time or runtime. Okay, so it's dynamic in the sense that the variable can have any kind of value, and the type check can't be done until we're actually accessing the specific current value. Now, since we have constants, the current value is going to be the value that it's defined with or it's constructed with, but it's still done dynamically in Scheme. So this is a very common approach in all interpreted languages because interpreted languages tend to just read through the code once or twice, and on that pass determine all the operations that need to be executed. There's not a lot of pre-compile into a secondary format and then execute that secondary format. With interpreted languages, it's executing as it's reading the code, so there's not a lot of time to pre-evaluate all the different types. So to show you a difference here, or to demonstrate that Scheme has dynamic type checking, let's just create some variables here. We'll say define A to be hello. We'll define B to be space world. Then we'll display them. So display A, display B. Display is for printing things, as we've seen. And then let's cause a runtime error. So is A less than B? Okay. So, oops, sorry. I should just save that before I create my videos so it doesn't keep happening. But for now, let's just run the code. All right, and the output here is telling. So we get hello world printing out to our console in purple, which means the displays worked. So defining A, defining B, and all that, the code was running through lines 1 through 17 was fine. It wasn't until we got to line 18 where we tried to use those variables in an inappropriate way. At that point, the dynamic type checking comes through and says, well, the less than operation should only be working on number types, real values or anything simpler like integers. But we were given a string, so that's a problem. So it goes into this variable, says the type of that variable is wrong, and then we get our error. So Scheme is using dynamic type checking here. Now, notice what this means is if we have branches in our code, we'll talk about conditionals in a future lecture, in a future video. If we have conditionals and a branch of code is never executed, if that branch of code has a dynamic type error, but it's never used, then there's no problem. The code won't crash, it'll just never actually run into that error. So, two different types of type checking, many different languages, and reasons to choose both, honestly. Okay, one last thing for this video. I/O in Scheme, so inputs and outputs. Fairly straightforward. We've already seen display, so I could say display plus 74, for example. Display takes in any kind of value, and we'll just, oh, sorry, let's get rid of this. Display takes in any kind of value and just displays it to the console. Okay. Notice in this case it has display hello, display world, and then display 7 plus 4, so it displays the result of that combination. But notice that it didn't put a new line anywhere in there. If we want to have new lines added to our code, we can either print a /n, so this will work here if I said /n like that. Run this, so we get hello /n and then the world on a new line. Alternatively, if we want to have a new line between our code, or just without having to print it, so for example, when we have numbers, it's kind of hard to put a string into that number, we can use the new line operation. So new line is a function that takes in no arguments, so you still need the brackets that says execute the new line function, and that just prints a /n to the output essentially. Okay, so that's output. If we want to do input, the primitive or the function is read. So we'd say define user input to be read. Okay, and if we run this, notice it gets to that line and then it brings up this prompt and it's just waiting for us to type something. So I'll type in 1 2 3 4. Okay, now if we ask what's the value of user input, it has the value 1 2 3 4. Okay. Ooh, did I skip a? I did skip a spot. All right, well, it bleeds in nicely here anyways. So the user input here, we've typed in the integer 1234. It's important to point out that the read primitive dynamically, or as you're typing things in, or as you hit enter, it will determine the type of expression that you've entered and will properly store it in that type. It doesn't just take everything in as a string, as Python does, for example, and then have to rely on the coder to eventually change that or to cast it. It just takes in whatever type. So if I ask, is this thing a number? User input, that returns true. So number with a question mark here is a predicate function, a function that returns true or false. And in this case, it returns true if its argument is a number, any kind of number, integer, real, rational, all of those, and false if it's not a number. And there's similar operations for booleans, strings, lists, and lots of other ones. Specifically, rationals and reals are complex as well if you want to go to those. So all these different type checks here, I'll just do a couple more here. So I could ask, for example, is there a boolean? Is this a boolean? And that's true because it is a boolean, even though it happens to be false. We could say, is this a string? And that's false because user input was holding the integer 1 2 3 4. So all these different type checking predicates can be useful as we move forward. And just one last thing to point out, just a naming convention here. The question mark in the function name here is a convention in Scheme that says this function should return true or false. This is a predicate function. It's only going to return a Boolean value, and we know that by the question mark at the end. It's similar to how other languages use is in front of whatever they're trying to get, is Boolean or is number. All right, I think that's it for this video. Nice short one here. In the next video, we'll learn about creating procedures in Scheme, and I will see you there.